All right, so far I have my complementary solution in here. I have my values in here. I formed my auxiliary equation. I found my roots. It was plus or minus 10i, so it's complex. So I have that complex form here. Here alpha is 0, beta is 10. Any questions about the complementary solution? I'm kind of happy to see sines and cosines, right? Why is that? Right, I expect my spring to oscillate back and forth, so that kind of makes sense. Happy to see that, right? All right, now let's apply our conditions. Okay, if x of 0 equals 0, then this thing turns into 0 equals c1 times 1 plus c2 times 0, so it looks like just c1. I gotta take the derivative of this guy next. The derivative here is going to be c1. Derivative of cosine is negative sine of 10t times the derivative of the inside function is a factor of 10 plus c2 derivative of sine is cosine times the derivative of the inside function. Apply my condition, tells me that 0 is equal to 0 plus 10c2. So what is my solution? What's my solution? Yep. X equals 0, right? Does that make any sense? Sure it does. Look at my initial conditions. If I start at rest and there's no velocity, what's going to happen to my spring? It's going to stay at rest, right? One of the ideas when we look at these models, these applications, is this is where our modeling, our mathematics meets the real world. That initial condition makes absolute sense that I would have a value of x equals 0. This thing is not moving. And what would be an initial condition that makes more sense? How would I modify this initial condition? I'm sorry, because it's right now x of 0 equals 0. I want to grab the string and I want to pull it, right? I want to pull it down somewhere, or up somewhere, push it up somewhere, and then release it. When I release it, at the moment I release it, the velocity is still going to be 0. Some velocity will be gained as the force using acceleration changes the velocity. So I'll move it somewhere. It will start at some different position, have a 0 initial velocity, and then it will go, and then I expect to get a non-zero solution. Okay? But so far, everything kind of should match our expectation. All right. So if we change this to x of 0 equals 1, then what do you get? Well, over here, I would get 1 equals c1. And then the second piece would basically be the same, right? So now I have a solution that looks like x equals cosine of 10t. Well, that makes sense because I expect this thing to oscillate back and forth. And it's a cosine instead of a sine because I'm starting up at a value of 1 here. Okay. All right. Let's visualize this thing. All right. Got my mathematical notebook opened. Here's my differential equation, mx double prime plus k times xt equals 0. I'm just desolving it. I'm doing the fancy stuff to store my solution. I'm going to run this guy. It has the crappy initial conditions in there. So I get my 0 solution. I change that guy to 1. There's our expected solution here, right? Now what does this actually look like? Here's my little model. Okay. So what is this? This is the object attached to my spring. It's initially at a height of 1, right? Has initial velocity of 0. This is the solution curve, right? This is the solution curve cosine of 10t. Right? So as time changes, I'm marking the point that I'm at, but the function value is giving me the height position of my spring. So when I put this thing into motion, you can kind of see how the solution curve relates to the actual motion of the object. Any questions here on what this manipulator is doing? Yep. Yeah. It's actually not too bad. You could probably write this or put it together. Not too bad. All right, so now we got this motion. Is that how springs move in real life? They just kind of go back and forth forever. That'd be an amazing world, right? But there's a problem. We're not really accounting for all the forces, right? We have other forces that are going to affect the motion here. One force is just a resistance, air resistance, right? Some sort of resistance of the surrounding medium being applied to our object that's moving through space here. So we need to add a new force into our equation. What force can we add? We've already accounted for the force for related to the position of the object. But there's another force, the velocity of the object. What does that mean? You know, last time you were in a pool or in water, you're walking in water. Walking around, walking. When you want to run somewhere in the water, right? You're trying to run, it's like, you get that resistance from the water you're traveling in. Right? Or if you move your water, your hand on the water, and you move fast. Right? You move slowly through the water. If you move fast, the water resists you more. Right? The force of the water acting on your hand is proportional to the velocity with which you're trying to move your hand through the water. Okay? So this is a force that's proportional to velocity. So how do I add that into my equation? Well, if the force is proportional to velocity, which is x prime, it's just equal to some constant. I'm going to call it d times x prime. Okay? So I've added a new force into the situation. Once again, why negative d? Well, because it acts against my motion, right? My velocity here, the medium is pushing against my direction of motion. That is a new force that I'm adding here, okay? So now I'm going to delete my work from the previous problem here. I'm going to grab all this stuff. I'm going to delete it to give myself some room. Okay. Now we've added this new piece in here. Now I got to modify this line, right? I'm really kind of writing as the general differential equation of mx double prime plus dx prime plus kx equals 0. A more complicated differential equation, but still just a second order differential equation. Okay. And it's very reasonable to assume that these constants or these coefficients are constants, right? Because the property of the medium isn't necessarily going to change. The property of the spring isn't necessarily going to change. So it's reasonable to view this as a second order differential equation with constant coefficients that we now know how to solve. Okay? All right. So now let's put another value in here. We have to have a value for d. Let's let d equal 1. If d is equal to 1, now what do I get? Well, now I get x double prime plus x prime plus 100x equals 0. We have a lot of extra time, so I should just make your hand solve that, but I'm not gonna. Right? It's not that bad, but let's just factor that into our model up here. If I add a value d now equal to 1, and I put that into my differential equation right here, dx prime of t, oops, I should probably say d times x prime of t plus that guy. Okay. Now I get this thing. Okay. You know, there's some ugly numbers in there, but really, who cares, right? They're just numbers, right? If I really wanted to, we could probably just put a decimal in here. Maybe that would make people feel better, right? Well, what's really going on with this solution? What's changed from the last one? The last one I had cosine of t. It oscillated back and forth, right? Is this one going to oscillate back and forth? It is. I got sines and cosines. But here the difference is my complex value isn't going to be just 0.04 plus or minus 10i, right? What does that alpha value change? The alpha value adds that leading piece here, e to the negative 0.5t. How is that affecting my overall solution? Dampens it, right? It makes it smaller right here. That's going to be a very small number. I basically multiplied my result by some number that's getting smaller and smaller and smaller. Let's take a look at what it looks like. There it is, right? Now we play this guy. That's the action I expect, right? It has that dampening effect from that force related to the surrounding medium. Any questions there? Okay. So we've added that, we've seen that more realistic model, but this is just a second order differential equation, right? So in general, I can write it like this. Here's my general equation. I can solve it in general as well, right? What do we do? Well, the auxiliary equation. I'm trying to find the roots. There's the quadratic formula. It would give me the roots for it in general. Whenever I get to those roots, it's going to lead me to one of these solution forms. So these solution forms make sense with this physical model. Let's take a look at the first one. All right, if I got distinct roots, R1, R2. If those roots are positive, R1 is positive, R2 is positive, what does that tell me about my solution? What does that tell me about the object? Distinct roots, positive, yeah.
Wouldn't it be like increasing the spring?
Increasing, right, to infinity. It's like fluid and progressive commercial, right, which is when it does. You flip out space. That's basically what's happening with my spring object, right? It is being launched to space, getting bigger and bigger and bigger. Is that everybody else's model? It's not, but it turns out I can't get positive R values there. Why not? There are some assumptions I'm making about my coefficients. M has to be positive, right? I have to have a positive mass here. D has to be positive. I don't have a medium that's causing an acceleration here, right? The medium is going to be causing some sort of friction. That's that negative value. So the D term has to be positive. And then I have K also has to be positive, right? So those are all positive values. And if I remember that, I can look at the form of these roots. And I'm basically making the argument that R has to be less than 0, right? Does that have to be true? Well, this is R. I'm claiming it's less than 0. Let's kind of solve this guy, right? I'm going to multiply both sides by 2m. I'll get this. I'm going to add that d to the right-hand side. That. I'm going to square both sides. M is positive, K is positive, D is positive. Is this always true? All right, I'm in business. Okay? So it's really just justifying the fact that R value is going to be positive in this real application. If it's positive, then what does my system tell me it's doing? I'm sorry, if R is negative. If R is negative, then what does my solution say is going on with my object? You know, think about an example. If the solution was 2e to the negative 4t plus 6e to the negative 2t. As time gets big, what happens to x? Goes to 0, right? Because the e to the negative pieces go to 0. All right, let's see if we can simulate that situation, right? We go back over here. We choose a d value that I know to be given to that case, right? So here I have, you see positive values here, but if you multiply through this by negative, both of these will end up to be negative. So this is the negative distinct root case. All right, zip it back to the beginning. It goes, do. Right? Is this spring going to oscillate? No, there's no sines or cosines. This is an over-dampened situation, we say. It's basically too much dampening, so the thing just stops. Right? The spring just goes too fast and stops. It doesn't oscillate back and forth, it just goes to zero. Okay? And we can see that right from the solution of our differential equation. Any questions there? Okay, so that's that case. I've talked through that scenario here. All right, so let's check there. This is a dampened situation. Dampened situation. And we know this one right here, this is our, where it's oscillating. And really the alpha determines if it's a dampened oscillation or not. Right? If that alpha value is there, we have a negative alpha value, then we're going to oscillate and kind of go to zero. If that alpha value is zero, then we just have this unlimited oscillation that goes on forever. Okay? What about this case in the middle here? What do we expect to happen there? Well, I don't see any sines or cosines though. Right? So I really can't see where an oscillation would come from. I do have this positive value from t, right? That's going to increase the system, but compared to e to the negative t, is there going to be a bigger little impact from that t? Be a pretty small impact for that t. This is essentially going to behave like that dampened situation. This one's also going to crash to zero, okay? But I want to look at that cutoff point because really there is just a little cutoff point between this oscillation and no oscillation. And how do I find out where that is? Well, we really want to look at that quadratic. It tells us all the information we need to know, okay? For instance, I looked at the oscillating case. I said if alpha is negative, dampening oscillation. If alpha is zero, then we have infinite oscillation. Skip any cases there, right? Skip alpha is positive. Can alpha be positive here? Well, where does alpha come from in that quadratic formula? Alpha comes from, if you rewrite this as negative d over 2m, right? And then you have the plus or minus the root stuff over 2m. This is our alpha. And once again, if d is positive and m is positive, this value is going to be negative. So we're going to have that negative alpha. Now, what determines whether we're in one of these cases? It's this piece. It's the d squared minus mk piece, 4mk, right? If we have a negative value under that radical, we're in the complex case. If we have a positive value in that radical, we're in the distinct root case, right? The repeated root is the one that's in the middle. It's when there's zero underneath that radical. So when does that occur? Well, we just set this thing to equal to zero, and we can figure it out, okay? So for instance, if I have m is equal to 1, if I have k is equal to 100, what would the value for d be that would give me in that repeated root case? If d squared is equal to, or minus 400 equal to 0, looks like d is equal to 20. Okay. So let's take a look at that value. D equals 20. There it is. I see my repeated root case there. I see that extra factor of t. We look down at the system. There's my system. Let's play it. Whew. Crash. Right? Now that might seem uninteresting, right? So I'll just crash down like other cases. There's actually some interesting stuff going on here. If I slow this guy down quite a bit and then play it, you notice that it's coming down, it's going a pretty significant distance, but as it gets down to the bottom, it slows down quite a bit. Now it's going slower and slower and slower. It's still traveling downward. I don't see the solution over here. I know those are small values, but it's still traveling down, but very slowly. Yeah, here comes the actual measurement on my solution curve. Okay. So what's going on here is that I am crashing towards that zero value, but I'm asymptotically approaching it, right? And that's actually pretty important. There are lots of cases where we want this spring effect, but we don't want the oscillation, but we do want a gradual decline down to zero. And so we can adjust maybe our K, our spring choice even, to affect how we approach that zero, right? Where would that be really important? And maybe something like shocks or something for a system. You don't want oscillation on your shocks, right? But you want this thing to come down and dampen as you get down. Okay. That could be an engineering application. Okay. Any questions there? All right. All right, so that's the big idea. Now, what else? In this case, we really fixed K and chose D, probably the other way around, right? You probably have D fixed from your surrounding environment, and then you choose K, you choose the spring you want to use in your mechanical system to give you the right effect, right? If you choose a different spring, you get a different action here, okay? All right, any questions? Any questions from the quizzes that I returned?